A black hole is a region in space where the pulling force of gravity is so strong that no matter, not even light, can escape from it. As a result, we cannot directly see black holes. In this lab, we will be observing the motion of a star with a known mass orbiting around a black hole located at the origin. The objective of this lab is to analyze the star's trajectory in order to calculate the net force acting on the star and to ultimately estimate the mass of the black hole. This experiment is important because black holes can't be directly observed. The presence of black holes is detected by observing their effect on matter around them, such as stars and gaseous nebula. Using a computational model, I found that the mass of the black hole was equal to 6.5 times 10 to the 33rd kilograms. The net force acting on the star due to the black hole and the net force components are summarized below. To analyze the star's motion, we will apply the momentum principle, which states that the change in momentum is equal to F net times change in time. Momentum can also be written as the product of its magnitude and direction. When taking the derivative of this equation with respect to time, results from the equation show that dp dt can be broken down into parallel and perpendicular components. An object speeding up or slowing down correlates to dp dt parallel changing due to a non-zero F net parallel component. Likewise, an object changing direction correlates to a dp dt perpendicular changing due to a non-zero F net perpendicular component. Thus, dp dt parallel plus dp dt perpendicular is equal to F net. Another fundamental principle in this lab is Newton's universal law of gravitation, which states that all objects attract each other with this force of gravity. This force is directly proportional to the product of the object's masses, and inversely proportional to the square of the distance between their centers. In GlowScript, my email generated this unique trajectory of a star orbiting around a black hole. In the program's initial conditions, I put the gravitational constant g and set the mass of the star equal to 2 times 10 to the 30th kilograms. The time interval between data points was set to 1 day, which is 86,400 seconds. This first while loop calculates the velocity of the star as it orbits around the black hole. In this portion of the code, the second while loop will calculate the net force acting upon the star and estimate the mass of the black hole. These lines of codes define initial and final velocities of the star. Then, the initial momentum and final momentum are calculated by finding the product of the star's mass with the corresponding velocities. The change in the star's velocity and momentum are then calculated by subtracting their respective initial values from the final values. Given a short time period, changes in momentum over change in time is equal to dp dt. By Newton's second law, F net is equal to mass times acceleration, which can be rewritten as change in velocity over change in time multiplied by mass. This is equivalent to change in momentum over change in time, which is equal to dp dt. The parallel component of dp dt can be written as the product of its magnitude and direction, which is equal to the change in momentum over change in time multiplied by the initial momentum divided by its own magnitude. As shown by Newton's second law, F net parallel is equal to the change in the parallel component of momentum over the change in time. Because dp dt is equal to the sum of the parallel and perpendicular components, dp dt perpendicular can be written as dp dt minus dp dt parallel. Again, by Newton's second law, it is shown that F net perpendicular is equal to dp dt perpendicular. Now that we have determined the net force exerted upon the star by the black hole, Newton's universal law of gravitation can be rearranged to find the mass of the black hole. Running the code, we find that the net force exerted upon the star by the black hole is equal to 7.7 times 10 to the 28th newtons and is represented by the orange arrow. The blue arrow represents F net parallel, which is equal to 6.91 times 10 to the 28th newtons. The average of all of the estimated masses of the black hole at each time interval is taken, yielding a mean estimated mass of 6.5 times 10 to the 33rd kilograms. The net force in its parallel and perpendicular components are equal to the rate of change of momentum in its parallel and perpendicular components. However, they differ conceptually. The net force and the change in momentum have a cause and effect relationship. A non-zero net force is a cause that results in the effect of a change in momentum over a period of time. A non-zero net force along the p-hat axis will cause an object to speed up or slow down. Likewise, an object traveling in a curved trajectory is the physical manifestation of a non-zero net force acting in the perpendicular direction, along the n-hat axis pointing towards the center of the turning circle. Hypothetically, if the current black hole was replaced with a different black hole in the same location, and the motion of the orbiting star remained unchanged, with only the force of gravity exerted upon the star by the new black hole acting upon the star, we would not be able to distinguish it from the original black hole. Based on Newton's universal law of gravitation, the mass of a black hole will remain constant as long as the net gravitational force, the mass of the star, and the distance between the two centers of gravity do not change. Since the star and its motion remain constant, this is evidence that none of these factors changed either. In conclusion, using the momentum principle and Newton's law of universal gravitation, we were able to estimate the mass of the black hole using momentum and velocity data, and the mass of the star orbiting around it. In the computational model, the estimated mass of the black hole varied slightly over time intervals, but overall remained fairly constant. To improve the accuracy of the model in the future, we could decrease the amount of time between data points.